Okay, so we're going to be recording this part of the session also. If anybody has any objections with the recording, please say so now. Okay, so now that we've talked about the magnetism, magnetic effects, magnetic fields, forces on moving charges or particles through magnetic fields. Now we're going to go through a few very important laws or principles related to electromagnetism that actually take us very naturally to some very interesting applications of electromagnetism. And the first one that we're going to see is what's called the Hall effect. Okay. And this was discovered in 1879 by a person, I believe he was a physicist. Who has, or what house had Hall as their, anybody have Hall as their, for your presentations, for your plays, I'm sorry? Does anybody have Hall?
Yes, we did.
You guys
Electric
did.
vehicles. Yes.
Yeah, you guys had Hall. Was he I don't remember, was he a physicist? He was probably a physicist, I think. His discovery was very important. It's called the Hall effect. And summarizing, and to make things simple, what is the Hall effect? If I have a conductor, okay, I have a conductor where a current is going through the conductor. Okay, current is going through a conductor. And then I put a magnetic field that's perpendicular to that current. The particles, the charged particles, electrons that are moving through the conductor, that would normally be moving through the conductor from point A to point B. Once I submerge the conductor in a magnetic field, there's going to be a realignment or a pull of these charges towards the borders of the conductor. Why is that? Because we just saw that if I have a conductor and I put a magnetic field in the conductor, there's going to be a force that's going to be exerted. So the charges are going to go to the borders, and because we're going to have charges in the borders, there's going to be a voltage that's going to be generated that's going to be perpendicular to the movement of the current. That's small voltage. It's called the Hall voltage. And there's an experiment actually that this guy did with regards to this effect. And it's used for many, many applications in real life. A lot of them that you interact with day to day, and you don't even, you probably don't even notice it. And so basically what we see there in the image, again, is that we have a conductor, okay? Let's assume that we have a plaque here. In this example, the conductor isn't necessarily seen as a wire. It's seen like kind of like a plaque of a certain material that has a certain density, charge density. And we've got a current that's going through the material. That's represented by I. It's going through the material from one point to the other. And then we've got a magnetic field that's perpendicular to this flow of current. In this case, the magnetic field is going upwards, perpendicular to the movement. And so again, because of the forces that are being exerted, we're going to automatically have charges or electrical force build up in the periphery of the conductor, perpendicular to the movement of the current. And since we have charges accumulated here on each side, then there's going to be a very small voltage that's generated there. This voltage is called the Hall voltage. The Hall voltage is going to be given by a certain relationship, which is first off the current that's going through the conductor, B, the magnetic field, divided by NED. And what does NED mean? N is the density of mobile charges, and E is the electron charge, and D is the distance, the thickness of the material. So you guys have already taken your materials properties classes. So different materials have different charge or mobile charge densities. Okay, so it's not the same if we have different types of conductors, they're going to behave differently. So the Hall voltage is going to depend on the material, the current that's going through the material, as well as the magnetic field and the density of the charges. And this voltage can be calculated. And we're actually going to do a lab experiment relating to this. Okay. And so this is the Hall effect. And the Hall, what's usually used to measure magnetic fields, it's called a Hall probe, which is basically this piece of conducting material that's placed within the magnetic field. And we used a voltmeter to measure what's called the Hall voltage. And once we have the Hall voltage, and if we know any of the other variables, we can find, for example, if we know the current, we can find the value of the magnetic field. We can, if we have the magnetic field, we can find the current, and so these can all be related. So this is what's called a Hall probe. So what we see there is that we've got two poles generating a magnetic field. So the magnetic field is generated between these two round things here. Imagine these two are the magnets. They're generating a magnetic field that goes from left to right. Then we've got the small piece of film. In this case, the material is important. It's a copper film that has a thickness D. It's very, very small thickness. In this case, it's very small, in the order of micrometers, about 100 micrometers. A current is made to go through the thin copper film, and we measure the voltage perpendicular to that current. In this case, and you can go to the web page and do some calculations there. But in this example, assuming that we've got a small film there, copper film. If it's copper, then N, which is the density of electrons, is 8.47 times 10 to the 28. That's a constant for copper. Depending on different types of materials that we would be using, then we would have different concentrations of electrons. So assuming that we had 1 amp and a magnetic field of 1 Tesla, and we already mentioned that the D, or the thickness of the film, is 100 micrometers, then the Hall voltage, which is calculated with the expression that we mentioned before, would be approximately 0.73 microvolts. It's a very small voltage that's generated. You've got the link there on the bottom. You can play around with these values. Again, they're going to depend on the material, and it's going to depend on the material, the current, that's going through the film, the magnetic field, and the thickness. Okay. Now, how can this effect be used practically? Well, I believe you agree, or you see, that if I change any of these parameters, the current, the magnetic field, the thickness, or even the material, then the Hall voltage is also going to change. And so this very basic principle in magnetism, this Hall effect, can be used in practical applications. And there's something called the Hall effect sensor, which are sensors that are usually used for some sort of magnetic switching, or to be able to identify the magnetic, to be able to identify movement. these are the applications of these Hall effect sensors. I believe you researched a little bit about Hall effect applications a few weeks ago. So the Hall effect sensor, what is this? Basically, it's going to be an application of the Hall effect where we can convert or take advantage of this principle to be able to measure something. So I'm going to throw around here some concepts that are important concepts in instrumentation theory. So you guys are probably familiar with the term or concept of a sensor. What is a sensor? A sensor is going to be something that senses something, it measures something, it tries to detect something. And we have various types of sensors that we use. Now, a sensor is also used, or the term sensor is also used in relationship with another term that's called a term called a transducer. Now, what is a transducer? A transducer is something that converts one type of energy to another type of energy. Usually transducers, or the type of transducers that we convert into sensors, because a sensor isn't anything, as I mentioned, isn't anything else than something that measures something or detects something. And sensors are based on transducers that convert one type of energy to another. Usually what we're trying to do is to convert type of energy A into type of energy B. And usually type of energy B usually is an electrical type of energy, okay? So when we have what's called a Hall effect sensor, like the one we see here in the image, it's going to be a sensor that is going to be able to detect changes in a magnetic field. So any sort of magnetic field that's around the Hall sensor, if that magnetic field changes or moves or gets larger or smaller, then the sensor is going to proportionately generate, because of the Hall effect, a voltage or a current that's going to be proportional to that change in the magnetic field. And so basically, that is the concept of a transducer. It's changing a movement type of energy, a kinetic energy, into an electric or electromagnetic energy. There in the web page, you can go deeper into studying about these sensors. The purpose of this course isn't to get into electronics applications. That's going to be next semester. We're just talking about the principles here. So when we get to electronics, we understand how they work. And so there's a typical sensors, like what are called LDVTs or LVDTs. These are these linear sensors to be able to detect movement, or solenoids or relays or other types of configurations that we're going to see later. So basically, how does the Hall effect sensor work? We have, again, a plaque, and this plaque is going to have a power supply connected to it that's going to generate a flow of electricity. And then we're going to have a magnet. And so remember this, in the Hall effect formula, this is what generates the Hall voltage. So if I have the current fixed, I also have the material fixed, but I can make the magnetic field change, then the Hall voltage is going to change. Now, remember that the magnetic field, or the strength of the magnetic field, has to do with or is also affected by distance. So the more separated we are from the magnetic field source or the magnetic field lines, there's less density. Therefore, the magnetic field is going to be weaker. And so if I can generate a configuration like the one I just showed you, where I can have the plaque that's generating current, and I have a way to measure a voltage, and then I've got a magnet. Notice that if I move the magnet, then the magnetic field is going to be changing. Therefore, the movement of the magnet is going to detect the is going to be detected, and it's going to be proportional to a change in the voltage. Okay. Um, and this very simple principle is used in a lot of applications. Some of the applications have to do with automotive safety. So the when you put on your seatbelt, there's a belt buckle, right? That kind of fits in and holds you in place. Now you've got your airbags in your car. And so when a collision occurs, there has to be something that detects, there has to be many things in the car that detects that a collision occurred, and that a certain, and that collision has to deploy the airbags and other protection systems in the car. So one of the ways in which a Hall effect sensor is used is, do you notice that, what, can somebody tell me what happens with your seat belt? So you put on the seat belt, but what happens when you try to move forward? What's the mechanism that acts in the seat belt? And how does the seat belt protect you when a collision occurs? Without talking yet about the airbags. Can somebody tell me how that effect occurs? What happens when you click on the seatbelt and then you try to move forward? What reaction do you feel?
Well, you have the two sections, the bottom section and the one that goes through your body, like through your chest, and the
Yeah.
one that goes through your chest is like more flexible, and the other one is more like hard, you could say.
Mhm.
And
Go ahead,
and
go
also,
ahead, please.
if you move slowly, it allows you to move, but if you make a sudden movement, it tightens up.
Perfect. Thank you, Renee and JC. Perfect. So you described it very well. It allows free movement for you, but the moment that you kind of make a sudden movement or something pulls, it contracts, right? Well, if I put a Hall sensor or some sort of configuration of a Hall sensor into the seatbelt mechanism, when there's a sudden movement, which the sudden movement is created by either the movement of the plaque through the magnetic field or the magnetic field through close to the plaque, and it's close to the seatbelt. Whenever a movement is generated, we're going to create a voltage here. That signal is sent to that sudden movement signal that the Hall detector um, uh, um, that the Hall sensor detects. That small signal is sent to other systems in the car to be able to deploy the airbags. Okay, because the airbags, you don't necessarily, you don't know when you don't know in which part of the car the impact is going to come. Do you agree with that? The impact can come from any place in the car. So, okay, I'm going to put a bunch of sensors all over the car. So if it hits, if it's being hit by something, the deployment occurs. Well, actually, the deployment should occur whenever the seatbelt has a very sudden reaction that reflects an impact. That's when the deployment of the airbag should occur. So the Hall effect sensor detects that. Because remember one thing, what we're detecting with the Hall effect, we're going to be detecting a change in any of these variables. This is important. What we're detecting is a change in any of these variables. And again, the variables that are fixed right now are going to be probably the material and the current. And so the one that we're varying is the magnetic field. So in other words, in the image that I just showed you here, in the image that I just showed you here, if if this is static, then the Hall voltage is going to be one fixed voltage. But if I move the magnet somehow, then I'm going to see a change in the voltage. That change is what we're detecting. Okay, so automobile safety is one example. Many appliances have certain magnetic switches and sensors to detect things. Fluid monitoring, this is interesting. This is interesting. Imagine that This plaque here, this plaque that we have here, is a very thin film that can move. So it's something flexible. Okay, imagine that that plaque is something flexible. And so imagine that now I have a flow, a certain flow that's going through here. And if the flow is larger, then there's going to be a diaphragm that's going to move. So it's going to be moving. Okay. So somehow there's going to be a movement in the film or the diaphragm. That movement, again, is a movement or a change in the interactions with the magnetic field. And so if I can detect that movement of the diaphragm through the Hall voltage, I can relate that to the pressure of a fluid. Okay, I can detect that with the pressure of a fluid. And also the Hall effect is used in many sorts of sensors that detect movement or any sort of thing, and that's being used a lot in building automation or automating houses or different structures. Okay, let's okay. So questions up to this point. Just an example of the Hall effect.